Welcome back, ladies and gentlemen. In this video, we're looking at work done by a variable force. This is an idea that's not going to be all that difficult, I think, but you'll have to remember a couple details from concepts that we've already covered. For example, related to springs, and also something related to way back in kinematics. We did a little trick with a graph that we looked at to learn some new information. So we'll get to that. First, variable forces. What kind of force varies depending on where you are? So that's what we want to first kind of look at. Variable forces. What might we be talking about? Well, it could be spring force for sure. And in fact, this is the one we're going to focus on for the bulk of the video. But well, check it out. I mean, if I have the spring and I pull a certain distance, then the spring wants to return with a certain force. If I pull a greater distance, the spring is pulling back harder and harder the more I pull. But we could look at that also, the strength of my pull, the force I must apply. And since there's a distance traveled by that force, then there's an amount of work done. But as the distance is traveled, the amount of force is varying. It's changing. So that's kind of what we're getting at. So you imagine, well, remember with springs, if you take the spring force and graph it against the displacement of the spring, you typically get something like that. As long as the spring obeys Hooke's law, right? This is a Hooke's law situation. So the more the spring stretches, the more the spring wants to return. It's got that restoring force. Okay, well, that doesn't help us yet with work. But the spring force definitely varies. What about a pendulum? So check this out. We have not studied these yet. So if you have an object suspended on a string, for example, and you pull it sideways and you release it, well, it's going to want to come back to this position. So there is a restoring force somehow trying to bring it back. If we displace it further, then that restoring force is larger. And so, you know, it is a little bit of a variable force. Displace further, it wants to come back more. That's kind of a non-physics way of describing it. There's another one, and we will study this one in further detail. Gravity, the force of gravity. Now, we're not talking about, say, little g, acceleration to gravity here on Earth's surface, or even mg, the weight of an object. We're talking about the force of gravity exerted between large astronomical bodies, which might be between the sun and the Earth, for example. There's a force. Newton's third law, action-reaction. So the force of gravity acting on Earth caused by the sun is the same as the force acting on the sun caused by Earth. But if there's a planet much closer to the sun, like Mercury, then it's experiencing a force that would be stronger because it's much closer. The strange thing is Mercury also has much less mass, and so that will affect the amount of force also. We're going to study the details of that later, but basically gravity also does vary with position. Depends on where you are. But okay, so that's great. However, we haven't talked about work yet. So here we go. How can we look at work done in a graphical way? Okay, so graphically, I'm going to have a graph. And what I want to do is I'm going to borrow a technique that we first saw in kinematics. I'm going to say, well, I'm going to graph force measured in newtons against the position measured in meters. Okay, fair enough. Now, most forces typically are constant, that we've been dealing with anyway. So I've got a constant value of the force. And what do I learn from this? This is not helping me with my variable force idea. Spring forces aren't constant for sure. This thing is getting harder and harder and harder to pull. That's not a graph of the spring force. But look at what we can do. This is a constant force here. What about the slope? Does the slope tell us anything? We've got a graph that looks kind of linear. Can we learn something about the slope? Well, slope in this case, slope is, I don't want to use m for slope because it's all mass in meters and everything else. So I'll just write slope. Well, it's rise over run. So I have a change in force values divided by change in position values. Does that tell us anything? Well, the units, maybe looking at the units is going to help. Newtons divided by meters. Newtons per meter. Well, that certainly isn't work, is it? But work does have newtons and meters in it. So there's another thing to look at, and it happens to be the area under the curve. So this is a rectangle. It's very easy. So the area of a rectangle is just length times width. And so what are we going to get? What does length times width equal here? Well, we have the amount of, let me change colors real quick, get something bright. We have the amount of force, and we're going to multiply that. To find the area, we're going to multiply that by the amount of position change. Okay, and that'll ultimately looking for the area under the curve, right? But the amount of change in position, well, that's your distance traveled. Oh, that's going to get us work. Okay, so the area under, it's supposed to be an R, sorry, got out of control, under a force position curve shows or provides the work done. Brilliant. Now, it turns out that's going to be true of any force position curve, even if it's not constant. So that's what we want to look at. Here we go. Typically with springs, plural, you've got a graph, force of the spring, you've got displacement of the spring from its resting length. So how much this position has changed from its resting length. You typically get something like that for springs that obey Hooke's law. With zero stretch or compression, you have zero spring force. If you have a certain amount, you get a certain amount of spring force. You double that amount, you get twice as much spring force. It's linear. Brilliant. But what we see is a triangle. So the area under the graph is still going to give us the amount of work done. But now the area is the shape of a triangle. Okay. Area of a triangle. 1/2 height times the base, or I guess it's usually written base times height equals the area. And so the area we're looking at, that's going to give us the work done by the spring force. And we have 1/2. The height, well, that's the change in spring force. And so from 0 to the top maximum spring force you got. And then the base is your change in position. Okay. But I remember something. Spring force. Also, I remember spring force is kx, where k is the spring constant and x is the same x. It's the displacement of the spring, either stretching it or compressing it. Okay, so can I just, you know what, I'm leaving out the minus sign. And the reason is, well, it's sort of unnecessary, right? If I have a spring, and I'm going to talk about the amount of work the spring does to return. Okay. Well, the motion is that way, and the spring is pulling that way, so it's kind of a positive amount of work done, right? If I talk about the force that I use to stretch the spring, well, the movement is that way and my force is that way, and so I'm doing a positive amount of work that way. When I move this way, what is the spring force doing? Negative work. When it goes this way and I hold it and it goes that way, my force is doing negative work. It's sort of arbitrary. This positive and negative is arbitrary depending on how you view it. So never mind the minus sign. Mathematically, it actually is not important. What we're going to do though is substitute kx into that guy. Work done either. Let's say work done on the spring to stretch it or compress it. 1/2 k x, there's my spring force, times x, or 1/2 k x squared. Work done by a spring force. And it turns out that this is a more or less the same relationship for the work done by any variable force, as long as it's a linear variation. If you see a linear relationship between the force and the position, then this exact same relationship works. You won't have a spring constant necessarily, but you'll have some other constant in here depending on what that particular situation is. Okay, so let's work that out then. What do we have? Got this example going, right? Find my notes here real quick. So we have a spring at equilibrium length, and you're going to stretch the spring a certain amount. I don't know, let's just make it a horizontal spring perhaps. Equilibrium length. And you're going to apply a force and pull that spring and stretch it. And the amount you stretch it is a distance x from its resting length to this new position, right? We know something about the spring constant. Oh, let's call this, I'll throw some scientific notation at you just in case it's been a little while. Spring constant is given as newtons per meter, right? Oh, that's crazy, because when I looked at this kind of graph and I found the slope of it, those units were newtons per meter. Does that apply here? Is the slope of that line newtons per meter? Well, this is measured in newtons. That's measured in meters. Slope equals newtons per meter. Slope equals spring constant. Hey, connecting ideas together. But back to this. So we have the spring constant, 3.5 times 10 to the 4th power newtons per meter. And the amount of stretch you give it, x. Let's call it 0.05. Throw another 0 in there for significant figures. We have 2 sig figs there, 2 sig figs there. Be consistent. So 0.050 meters. How much work do you do to stretch the spring like that? Here's what you do. Well, the work you do on the spring. Here's the wording. Work on the spring. Work done on the spring. 1/2 k x squared. Easy peasy. Most of you guys, I'm sure, maybe all of you guys, that you really don't have to see this example, do you? 3.5 times 10 to the 4 meters per meter. X squared. 0.050 meters. Must be squared. Handy dandy calculator. Squared times 4 equals times 1/2, 0.5. I get work done, 42.5 joules. Work is done, measured in joules. Work done on the spring. On the spring. Okay, fair enough. What about the work you have to do to compress it? Let's say you take it the other direction. Oh my goodness, what does that do for us? Sorry for all the noise. You're going to compress it by an equal amount. Well, now, you do that. And x is still 0.005 0.050 meters. Oh boy. So think about this for a second. The force you apply is in that direction, and the movement is in that direction. What is the angle between the force and your distance traveled? The angle is 0. So you should get what kind of value for work done? Should you get positive or negative value? Well, with the force in the exact same direction as the distance traveled, theta is 0, cosine of 0 is 1. You should get a positive amount of work done. Okay, there's another way of thinking of it. Even if I make that a negative value for x, I'm going to end up squaring it. X is squared. I'm still going to get a positive value for the work done. It seems to work out either way. And it turns out, so this was a stretch situation. Here is a compression situation. So when we compress it, how much work is done? Well, work done on the spring. That's what I should have been saying all along. This should say on the spring, not by the spring, but work on the spring. 1/2 kx squared. 1/2, same k, same x. 0. I'm going to squeeze it in, I promise. Squared, don't forget that exponent, do not lose track of it. You end up with the same answer. Work done on the spring. To compress it, same amount of work as it was to stretch it. Here's our stretched situation. All right, well, that's pretty cool, huh? This is work done on the spring, not work done by the spring. What do you imagine work done by the spring would be in this situation? If I'm pulling it away like this, I'm stretching it a distance x. Well, the movement is that way, but the spring is pulling backward. The spring force is 180 degrees away from the direction traveled. You should get a negative amount of work done. Cosine of 180 is -1. Okay, now how would that work out here? Ooh, boy. Well, you just do that. You put a minus sign in front of it. That's essentially the easiest way to do it. This is all, in this example, let me clarify this. Work done on the spring. And work done by the spring will be the opposite value. Will be -42.5 here, -42.5 there. All right. Well, that's it for now. Easy peasy stuff. Thank you for watching. I'll catch you next time.